Today we're going to look at a really unique piece of hardware, and that is what's in my hand right here, which is kind of heavy. This is the Tenstorrent Wormhole N300d. Now, it looks like a GPU with the fans, the overall footprint, and the PCIe in the bottom. However, this is different. While designed for AI and machine learning stuff, this is an AI accelerator. And what I mean by that is if we flip it around to the back, we can see that this board actually has two processors in it. Between them, there is combined 24 gigs of GDDR6 RAM, and it can be used to run local LLMs and things like that. Now, truthfully, I've been interested in this for a while and I've wanted one. I didn't necessarily have a specific use case in mind, so for today's video, we're just going to unbox it and play with it, and we will end up just kind of learning about some fundamental AI and machine learning concepts throughout playing with this card right here. So first look, the box art is actually kind of cool, but we see this is made in Canada, which is unique. There's some more like trippy wave patterns in there. And as we unbox it, we are met with our first look at the actual, I suppose, box. But in there, we have an important warning about the specific power cable we need to use, as well as a get started guide with some cool graphics. It is now time for the main event, where we can take a peek at the card for the first time. It is in an anti-static bag, as we would expect something like this to be. And when we go ahead and take it out, the first thing that we notice is it is extremely heavy. So this outer shell with the kind of honeycomb vents right there is metal, and it is rather dense metal. We can see the two fans are kind of pasted in there, and they do look pretty robust. It has the two processors visible, at least from the back like that, which lets us know that something is a little different here, as well as the power cord, and the front is not video output, but for connecting multiple cards. As it is now time to go ahead and place it in the PC, we make note of the importance of using the special cable that we need, and then following that, we just place it in like you would with any PCIe device, I suppose, and then screw it in. The next thing is just to go ahead and plug the power cable in just like that, and then we're basically ready to boot it up. Now that the card is physically installed in the system, it booted up and nothing seems super wrong. We are going to go ahead and fast forward a few steps. We have gone ahead, well, I have gone ahead and just kind of installed the software and the drivers and the firmware and things like that. So our next step is essentially going to be to go ahead and get our first, I suppose, touch of the card. Now, this may seem somewhat familiar to those of us who have used NVIDIA GPUs before, and I will explain more on that in a second. I am going to just go ahead and open a terminal window, and from in here, type TT-SMI. Now, those of you who are familiar with NVIDIA may be familiar with NVIDIA-SMI, so that should give you a little insight into what this will actually show us. And essentially, this is kind of a monitoring station, if you will, for the specific card in our system. I will say I am impressed with this. Just aesthetically, it's nice, and obviously things that run within the terminal don't have a lot of like graphical capability, so this is well done for the constraints of what it runs in, that being the terminal. As I digress, we do have just like some basic things. We have our host information, which is basically just the specifications and information on the system this is actually installed in. Mine is an Ubuntu 24.04 system with 32 gigs of RAM, which is a little lower than the suggested amount of 64, but we will make do. Following that, we just have our software versions and things like that. But the cool thing is kind of right here for 1, 2, and 3 that we have. And I do like the little slider effect there. But essentially, this just gives us detailed information about the card installed in our system. Now, this is one card with two processors in it. So that is why we see two processors right here. But a bus is only recorded for one of them because they are on the same card, which is just in one PCIe slot. So we have information about that, 12 gigs each, so this is a 24 gigabyte total RAM card, and the link speed and link width. So these are just kind of like technicals on the physical attachment of the card to the actual motherboard. Beyond that, we have our telemetry, which is kind of cool. We have core voltage, core current, clock speed, which I do believe that's what don't quote me on that, but it says CLK, so clock speed, core power, and then core temperature. Now, it is around 3 in the morning, but this was actually, I think, like the hottest day in history, or at least for a while in Massachusetts. So the ambient temperature in the room I'm in right now is still very high, even though it is in the middle of the night. Beyond that, our last thing is just kind of the device firmware versions, which we kind of see somewhat like as similar to this, but obviously for different things. With that, the only other thing that I kind of want to make note of is the dark mode toggle here, which it's nice to have, but I definitely prefer leaving this on in dark mode because this is kind of somewhat blinding, especially with studio lighting and stuff like it's just so I applaud them for having it. I would probably just keep it in dark mode like this. With this, I am going to go ahead and just click Q, which will close out of this, and we will move into the next step and phase of this, which is actually playing with this card. Now, this is something where I didn't really know what to do because the purpose for this card for me that I find interesting in it is that it is cool to kind of teach you about more lower level and core concepts about machine learning and AI and things like that. It is capable of running large language models, but that is something that is kind of, I think it would be boring to just watch me talk to Llama 3.2 11b, the vision model on this. So we are going to go ahead and actually run through a few examples that kind of touch upon more core concepts and foundations of AI/ML. To begin playing with this card, we are actually going to be using a container. Now, I'm not going to really go through like step by step how I got this working, but I do want to just reference what specifically is being used here so it makes a little bit more sense. So this is the TT installer, and essentially there is a one-line quick start command that kind of goes ahead and installs a lot of the dependencies and other things necessary to actually use the card into a container. So as we can see right here, it is installed as a container using Podman. Using the container is easy, just run this. So it just kind of allows us think of it like a test bench basically to play with the card within a contained environment, which is always good for experimenting. Now with that, I do have a slightly different version of this command that I'm going to be running just to go ahead and actually get into that container, but I did want to just quickly reference what is actually going on when I enter this command right here. So I will just go ahead and paste it in. I did have it copied, and I am now in the Podman container where we can kind of go ahead and actually start playing with some of these examples. Now that we're in this Podman container, the next step, and at least what I want to do and what my interest in this card is beyond just being something that's not like a typical GPU that can run LLMs, is educational. And what I mean by this is basically if we look at these documents right here for the latest version of the TT-NN docs, we can see there is a small tutorial section right here. And these tutorials essentially kind of give us hands-on examples in some of the concepts that are scaled up massively for actual LLMs and other AI machine learning models. Now, in following these tutorials, there are a couple of things that I want to mention just prior to that. First and foremost, what exactly is TT-NN, as we will see it kind of mentioned a lot here in the code and things like that. And really, I will just regurgitate what's listed right here, where this is a high-level Python API designed for developers to run models like Llama, Mistral, Stable Diffusion, and more on the Tenstorrent devices. So it is a high-level Python API to allow us to kind of interact with our device. Beyond that, we are going to see tensors brought up a lot here, and they do actually have a kind of article right here just kind of giving some pertinent information about what exactly the heck a tensor is. Now personally, I am not going to just kind of read through this and regurgitate it to you as I kind of scroll through it, because one, I don't ever like when people do that. I don't know, it makes me mad, but I think I'm in the minority there. But two, I don't think it would be doing anyone a service to speak authoritatively on these things right here. So with that, we are just going to basically say a tensor, or a TT-NN.tensor, is a multi-dimensional matrix containing elements of a single data type. And with that, we are going to just jump back to the tutorials to begin playing with our tensors. Now I have gone ahead and just pasted the entirety of this code right here into VS Code so that I can easily get it into the actual container. But before that, I suppose let's just go ahead and at least quickly browse through this actual kind of article and each snippet of the code, which we see here kind of leading up to the final output of the entirety of the script. So really, maybe I'll just go through it here because I have also done some learning as well. So basically what happens here is we're importing TT-NN as well as just something that will allow this to log the output of what we're doing here kind of in a pretty way. Now, I suppose it would be best to put this in a more casual way, but essentially what's happening here is we're giving this card two pieces of data and we're saying perform a mathematical operation on these pieces. However, these pieces are something that is very foundational and fundamental to AI and machine learning, which in this case are tensors. So we are giving it two tensors, each with a shape of 32 and 32, and then we're basically saying add these two together. So what we can see right here is the entire value of every element in this first tensor is 1, and the entire value of every element in the second tensor is 2. So with that, we are basically going to go ahead and have it add these tensors together, and then we will get our output. Now, it was kind of hard to grasp at first, I suppose, some of the foundational and like what you would expect to happen here, but ultimately the output of this is we will get a tensor with the value of 3 for every kind of item in that tensor shape. Again, I'm not a professional here, so bear with me. In addition to that, we just have our data type right here, which for this is using float32, which honestly for this very simple, like we're adding 1 and 2. I don't know that that's really necessary, but I'm not at liberty to change this. So in addition to that, the layout is just kind of the tile layout shape. So that's 32 here. And I believe that has something to do with some actual physical design of the card. So basically 32 is the most efficient tile size for this specific card to process everything in one clock cycle without needing to kind of be underutilized or needing to kind of, I think, batch things again. But I suppose I will say, what you see right here where I'm trying to actually explain this stuff, this is all a result of actually getting this card. And again, why I wanted it, because it gives you hands-on learning opportunity for some of these more complicated concepts, especially for those of us without like a education specifically in these things. So you can kind of get hands-on experimental learning. So with that, basically, as I'm probably talking too much, we're just going to go ahead and add these two tensors and the card will do the work. So really, I'm just going to go ahead and take this and I will paste it into this Podman container, just using Nano to actually create the file. So I'm just going to call it add.py. I know that's probably not what it's supposed to be called, but that's all right. And then basically I will type Python 3 and then add.py, and it will actually go ahead and add these two tensors together. And assuming everything went well, it will just show us this, where first it lists our first tensor where every value in this shape is 1, and then the second one where every value in this shape is 2, and then finally the result of the addition of these two tensors where every value in that shape becomes 3. Basically adding 1 plus 2. Of course, this is super simple. Well, at least when you think adding 1 plus 2. But again, this is like getting to look at a Lego block of something that is a core concept in like AI and machine learning. With that, there are now some more intricate examples that are kind of just right here. So basically, if we minimize this, in the tutorials we see there are 3 things. We just went ahead and created and added 2 tensors. Our next step is to perform some basic operations with TTNN. Now the next example is a little more complicated, and truthfully I don't even really want to talk about this, but it does kind of lead into the final example right here, as the final example references the prior 2 examples, of which we're on the second one right now. This is essentially, as said right here, this demonstrates how to create various tensors and perform basic arithmetic operations on them using TTNN. And again, this is kind of just like a walkthrough, these tutorials are, of some of the core concepts of AI and machine learning. This one in specific about some of the arithmetic that occurs. So I won't go through this verbosely, but essentially from my understanding here, this will go ahead and create 5 different tensors using various methods. I do believe the first 3 are just kind of standard methods for TTNN to create them directly on the card. The 4th, I think the host creates it. So like your system CPU would create the tensor, and then it would be moved to the card using the helper function outlined right here. And then the final one is just created using NumPy and then moved to the card, based off what I'm seeing right there in that line, assuming that's correct. So essentially this script will perform 3 different types of arithmetic operations. The first is just adding the result of 2 tensors together, which we actually saw in our previous example. The second is this mul underscore result, which is element-wise multiplication. So this isn't the full-on matrix multiplication, but The matmul result is the full-on matrix multiplication, which we can see right here, which it will perform with the other tensors. So basically, we will go ahead and just run this, and we're going to get a bunch of numbers outputted right here, but these will all correspond to a specific action here as denoted in this section of the script right here, where we see the results of these 3 different types of operations, and then we will also see this one. So now we're going to go ahead and run this example in our container. I do want to make note that the container did not have some of the packages installed that it needed, so I just had to go ahead and install Torch, and I just used the commands on the website for the installation of that. I suppose I'll just show it real quick just for good measure. Where basically when you click on this get started section right here, it gives you like a bunch of options. Now, being that we are not using an NVIDIA card, we are just going to click on CPU for the compute platform section, and then I just ran this command right here in the container. Beyond that, I just needed to install NumPy. I think I had it, but that would be something additionally that you likely would need. With that, we can go ahead and just run this script right here, and essentially it will go ahead and perform all of these different arithmetic operations. In addition to that, it first creates the tensors and then performs the arithmetic operations that are listed here. And basically that's kind of what we're seeing here in this output. For the first time in my life, the tiling feature in an OS did not just enrage me, but actually assisted me. So we do just kind of get the output. So this is our first tensor. This is our second tensor. This is our third tensor. This is our fourth tensor, which I do believe was moved from the host to the Tenstorrent card. And then this is our fifth tensor, which was created using NumPy. And then basically these are the arithmetic operations. So we have addition, element-wise multiplication, and then matrix multiplication. Following that, we have the simulated broadcast, the broadcast row vector, where I think, again, like as I'd mentioned, that's kind of like just a workplace policy that applied to all employees. The final example here is really quite cool because not only are we going to get our first experience actually running an AI model on this card, but we're also going to be training the model using our host system. So for this example, it says right here MLP inference with TTNN. MLP is a multi-layer perceptron, but really to put it in more like human readable format, this is essentially going to be using a data set of a bunch of handwritten numbers. So 0 through 9, there's a data set of a bunch of small pictures of people's handwriting having written any random number 0 through 9. We're basically going to make a tiny model and train it on that data set so that when it actually sees an example of one of those handwritten numbers, it can go ahead and correctly kind of identify the specific number that is being shown to it. Again, not scientific, but kind of the gist of this. So the first step here is and a little obscure. We have to kind of scroll all the way down because we need to first run this script to generate the weights for the example. And truthfully, that is kind of a simple way to actually explain the script because we are actually going ahead and creating the model here, loading in the data, kind of denoting the training structure. So for 5 epochs right here, and then kind of saving everything into this MLP MNIST weights.pt file. And then once that's done, we are actually going to go up here and run this example source code, which will actually take everything that we create with that model and kind of transpose it or change it into tensors for the Tenstorrent card to be able to understand and then perform inference on the data and then kind of output the result and then show it whether or not it got it right or not. So first and foremost, let's jump into running this script right here where we basically create and train the model. Now I have just directly copied that script from the page right here, and I am going to run it from within the Podman container. I don't know if that's best practice or not, but I figure it has the best chance of saving the weights in a location that will be directly accessible for like the actual inference script here. So with that, I'm just going to do nano train.py, paste it in, and then run it. Hopefully it works. I may need to have some other dependencies installed, but we'll kind of just see. Okay, so based off of what I'm seeing right here for this output, it is functioning properly, at least in terms of me not needing to have installed any more dependencies. And then basically we're seeing the loss value for each epoch. So as it goes down, basically this just means the model is becoming more performant. So it is doing a better job of identifying correctly what kind of like handwritten number it sees. And again, you may be like, well, hey, why didn't you use the card to train this? Or like, isn't training a model really difficult or like intensive? A tiny little teeny model like this is very capable of being run on a host machine like this, or in this case, this is a Core i7-12700K. So basically the CPU can handle a tiny little model like this, and it's not going to really break a sweat. If you were going to train like a larger LLM or something like that, you may get into a little more like necessitating beefier hardware. But I digress. So we now have the correct weight saved right here. And really our next step is to just go ahead and actually run the script that preceded the one we just ran, where essentially it will use the Tenstorrent card to run inference and actually predict the data that our model just learned from. You know what I mean, hopefully. So I will just go ahead and basically copy this in right here. And kind of as I was saying, this is basically just going to take this model that we just trained, kind of transpose it into a way that the card can understand the tensors, and then go ahead and run predictions on sample data and hopefully do it well. So I will just do, I know my naming schema is quite poor, so please don't hold that against me. But now if we do this, I should be able to Python run.py. I am wondering, maybe I should have TTSMI open in a parallel terminal just to kind of see. Okay, so probably we'll want some telemetry instead. And let's basically just kind of keep an eye on current, core power, and core temp as we run this, because we are actually going to be using the wormhole to perform assessments of this. Okay, and basically it is kind of like, it's not exciting visually here, but it is exciting psychologically, I suppose one could say, because while that did just happen super quick, basically it ran 5 different examples right here. It got them all correct, where sample 1, it predicted 7, and it was actually 7. And basically, yeah. So this did actually just perform inference using our wormhole card, using a model that we just very quickly kind of copy pasted, but created and trained on our host system. And then it was brought over to the card. It was kind of predicted using our card. And then it was just kind of put back into a way that it was capable of saying whether or not it correctly did this. So again, this is kind of, and this brings me more probably into the closing, but this was my whole interest in this card was, one, because it was kind of a unique and different architecture that could still handle running LLMs and things like that. But beyond that, just having simple examples like this that you can actually follow through and correctly run and actually see really at a low level what's happening is very cool. It's unique and definitely has a specific type of person who would be interested in this card. I will say it's not going to be super like plug and play. If you just want something to run LLMs on, this probably isn't going to be the most ideal option. But if you want something that really allows a fantastic, like deep level of exploration, this is totally cool. And I will say, this is just kind of scratching the surface of some of the stuff you can do. There's like GitHub and stuff like that. It's seemingly like a fairly active ecosystem and stuff for this, which is always kind of cool. And it's just neat and gives you a lot of low level and hands-on learning opportunities, I suppose one could say. So that's probably going to wrap this video up. Again, I was really excited to have this thing, and it is just going to be used as a learning tool like this. I probably won't be running LLMs on it and stuff like that, but I will be playing with it in terms of kind of this sort of stuff that we saw together today in this video. I will say that I suppose I'm fortunate in that I can be pretty transparent about my technical strengths and also weaknesses. So that's why I wanted this card, because I knew it would give me a little more insight into the foundational and underlying elements of things that, one, I use every day, and two, that I actually talk about on this channel. So I always want to make sure that, like, it's easy to just talk like, hey, this LLM is awesome, this is why I like playing with it, it's fun. But I also want to know like what's going on behind the hood and under the hood and things like that. And that was a big reason for getting this card. So with that, that is going to wrap up this video. I figured folks would be interested in seeing a different piece of hardware doing something that we're all very big fans of, which is like AI machine learning. So with that, thanks for watching, and if you have any questions, please feel free to leave them in the comments if they're not technical.